Hello student, welcome to our lesson 5, and in this lesson we are going to look at universal gas law. Now we start with the equation of state. We have that a general gas law relating the changes in pressure, volume and absolute temperature can be derived. Remember, through those experiments, that is starting from the Boyle's law, Charles' law, and now the pressure law, we have seen that there is a relationship between pressure, volume, and temperature. So we can try to combine all those three and now come up with one equation that we call the equation of state. Now we are going to consider a fixed mass of a gas which is being changed from state A to B through intermediate state C as shown in our diagram here. We have state A. This one is moving to state B, but it is passing through state C. So as you see, in state A, we have P1. Then we are told that we have the constant. During the Charles law, you have, it is moving to P1 because the pressure is constant. Then when you move using the Boyle's law, the pressure is increased, it moves to P2. Remember, in pressure law, pressure is not constant. That is, in Boyle's law, pressure is not constant. Then when you come to volume V1, in Charles' law, the volume is increasing to Vc. That is, it is coming from V1 to Vc. And then from there, using the Boyle's law, it is inversely proportional. Therefore, it is decreasing to V2. Then when you come to temperature, we have T1. Using the Charles' law, the temperature is increased to T2. Then using the Boyle's law, the temperature is constant. That's how now we have the T2, it is remaining as T2. So now we are considering that this gas is moving from A to B, but it is passing through this particular intermediate state. Now, from A to C, the gas is heated at constant pressure. You can be able to see that. It is heated at a constant pressure. That is using the Charles law. So, V1 over T1 is equals to Vc over T2. So we can be able to get the value of Vc here. Making Vc the subject, we have Vc is equals to, you just need to multiply by T2. So it will be V1 times T2 over T1. Then from C to B, the gas is changed from P1 to P2 at constant temperature. You can see that the temperature is constant. So again, now there we are applying the Boyle's law. And according to Boyle's law, P1 V1 is equals to P2 V2. But what we are having here, because we are changing from this now C to B, the pressure is coming from P1 to P2, the volume is coming from Vc to V2. So again, we have P1 Vc is equals to P2 V2. So making the V2 the subject, you get that it will be P1 Vc divided by P2. Remember, all what we've done is that we have divided through by P2. But now initially we had that our Vc is V1 T2 divided by T1. So we can replace, where we have Vc, we replace with this part. So by so doing, you'll get that it will be, remember now we don't have Vc in this one, we have V1 T2 over T1. So it will be P1, then V1 T2 divided by P2 T1. From there, as you can be able to see, we can be able to rearrange, and by so doing, we put all the values that have ones, or the initial temperatures, volume, and pressure on one side. And if you go back to that equation, it's like now we are dividing. In here, we divide through by T2, and then we multiply by P2. So it's how we are getting P2 V2 over T2. And then this side we are left with P1 V1 over T1. So you are trying to take all these P2s and T2s on this other side. And you'll do that by dividing by T2 throughout and then multiplying by P2 throughout. And that is how you are getting P1 V1 over T1 is equals to P2 V2 over T2. Now this equation shows that PV over T is equals to a constant, where now we are saying that it is equals to K, where K is a constant. And this now is what we call the equation of state. and K depends on the quantity of the gas. So the equation changes to PV over T is equals to R, where now we are considering 1 mole of a gas. But now this one, we have said that K changes, or it depends with the quantity of gas. But now when we are considering 1 mole, then this constant becomes R. And the constant R is the same for all gases and is called universal gas constant. This R is called universal gas constant. Now we proceed to examples. A gas R at 27 degrees Celsius and 750 millimeter hydrogen was found to occupy 36 centimeter cubic. Calculate the temperature at which the same mass of R will occupy twice the volume of the pressure of 1000 millimeter hydrogen. So again we have P1 as 750, V1 as 36 cubic centimeter, T1. Remember, all these temperatures has to be converted to Kelvin. So that's how we are adding 27 plus 273, which will give you 300 Kelvin. And then P2 is 1000. So V2 is 72. So we are looking for T2. So this will be P1 V1 over T1 is equal to P2 V2 over T2. So by so doing, you replace the values and you'll find that you have only one unknown. You can make T2 the subject of the formula by multiplying. You have this one times this one, then multiplied, we are cross multiplying this one, then multiplied by 300, then this one will be multiplied by this, so you will divide by 750 times 36. And when you get that, when you key these values inside your calculator, you get that the value of T2 will be 800 Kelvin. Then from there, we move to the kinetic theory of gases. Now, the kinetic theory of gases proposes that the molecules of gas are in continuous random motion. That one we found in Form 1, that these particles are not constant or they are not fixed, they are always in motion. Therefore, kinetic theory of gases states that molecules of gas are in continuous random motion. Then we have the basic assumptions. One, that the attraction between the molecules of gas is negligible. Remember here, we are dealing with ideal gas, and that is how what we said earlier, that the force of attraction between the particles of ideal gas is negligible. Then number 2, the volume of molecules of gas is 0. It is negligible. Then number 3, collision between the molecules and with the walls of the container are perfectly elastic. Then from there we can move to kinetic theory of gases and gas law. And in here we are going to consider the 3 gases. We have the Boyle's law. In this case we have the Boyle's law and kinetic theory. Now we have seen that when we increase the temperature, or when we make sure that the temperature is constant, a change in volume of a gas results in a change of number of collisions per unit time between the molecules and between the molecules and the walls of the container. As a result, remember now we are saying that when the temperature is constant, a change in volume, you are changing the volume of a gas, results in the change in the number of collisions per unit time between the molecules and the walls of the container. As a result, the pressure changes. Then from there we have the Charles law and the kinetic theory. Now in Charles law, we have that when the pressure is constant and the temperature is raised, the speed, or when you increase the temperature, the kinetic energy of the molecule increases, and therefore the molecules will increase the speed, causing them to occupy a larger volume. So because now they have acquired a lot of energy, they will vibrate at a higher speed, and by so doing you'll find that they will occupy a larger volume. Then we have the pressure law and kinetic theory. We have that a change in temperature changes the kinetic energy and hence the speed of molecules of a gas, and therefore if the volume of gas is constant, remember in pressure law the volume is constant and you are increasing the temperature, so you are giving those particles energy, therefore you increase their collision, and by so doing you find that the temperature will also increase as a result of change in temperature. Now, the pressure is caused by the collision between the molecules of the gas and the walls of the container. And that is why now we are saying, as you increase the speed of the particles, then what you're doing is that you are increasing the pressure, because the collision is the one that is giving us the pressure. Then we need to look at the limitation of gas law. Now, gas laws do not apply in real gases. That one we had mentioned earlier, that these laws, they only apply in ideal gases, because real gases liquidify, or they change the state from gases to liquid before the volume of the gas reduces to zero. Remember, when we talk of ideal gas, we are saying that at absolute zero, it is occupying zero volume. But now we are saying in real gases, at that particular temperature, that gas will already change the state before it gets to zero temperature. Then from there, we have an example. 20 liters of gas is kept at a pressure of 1 times 10 to power 3 kilopascals and 27 degrees Celsius. The temperature is lowered to negative 183 degrees and the pressure is increased to 2 times 10 to power 3 kilopascals. Then from there now you're supposed to get what? You're supposed to get the final temperature. We have P1 is equals to 1 times 10 to power 3. T1 is 27, you add 273, you get 300. Then P2, you are supposed to get it here. Then T2 is that one. So we are supposed to get the value of V2, not P2, but V2, because V1 is given as 20 liters. So we are applying now this one, the general equation that P1 V1 over T1 is equals to P2 V2 over T2. So by substituting the values, we can be able to make sure that we are able to get V2 as the subject of the formula. And we are doing that through by cross multiplication. If you cross multiply, you will get 1 times 10 to power 3 kilopascals multiplied by 20 liters multiplied by 19. And then this one will be multiplied by 300 Kelvin times 2 times 10 to power 3 kilopascals times V2. And then now to get V2, you're going to divide through by 300 times 2 times 10 to power 3 kilopascals. And this will cancel out the 10 to power 3 kilopascals. And now when you key in 20 liters times 90 divided by 300 times 2, you get that it is 3 liters. That will be the value of V2. Now we move to the second example. A container holds 80 cubic centimeter of air. The pressure is 100 kilopascals and the temperature is 7.5 degrees Celsius. What is the final pressure when the air is compressed to 30 cubic centimeter and the temperature is 29 degrees Celsius? So we proceed as follows. First of all, we write the values that we are given. These are the values. After writing the values, we have only one unknown, and that is what we are looking for. So again, we use our formula. We substitute the values because now we have them. We have P1 100, V1 80, then we have T1 280.5, P2 is what we are looking for. So by cross multiplying and again making P2 the subject of the formula, you find that your P2 will be 287.12 pascals. From there, we have example 3. The figure below shows dry gas trapped in the enclosed head of a horizontal glass tube by mercury. The atmospheric pressure is 750 mm hydrogen. What length of the tube does the trapped air occupy when the open head is raised until the tube is vertical with open head facing up? So we have this one. We are saying now what volume will be trapped when it is vertical. We proceed as follows. We are using the Boyle's law. P1 V1 is equals to P2 V2. Now P1, this one, will be equal to the atmospheric pressure. But the atmospheric pressure is given as 750 mm hydrogen. Then P2 will be now the sum because it will be vertical. This mercury will also exert pressure on the air. And therefore the total pressure will be 750 plus 250, which is 1000 mm hydrogen. Now our V1 will be 200 times A because A is the cross-sectional area of the tube. And our V2 is what we are looking for. It will be L multiplied by A, where L is now the length. Now, using now this formula, we substitute the values. P1 is 750, V1 is 200A, P2 is 1000, and V2 is LA. A's will cancel out as shown here. So to get now the value of L, it will be, when you multiply this and divide by 1000, you get that it will be 150 millimeters. From there, we have the assignment again. The assignment is testing what we have just covered. So make sure that you practice a lot, share with your peers, and that will help you retain the knowledge for a longer time. So thank you and prepare for the end of topic exam. Let us meet in another lesson.